In Concept X for honors students, we're going to be looking at calculations involving properties of light. Up until this point, we talked about basic electron configurations, how we produce a bright line spectrum, and now we're going to take that one step further by actually doing some calculations that relate to those concepts. So hopefully by the end of this lesson, you'll have a very basic understanding of some calculations that can be completed involving the energy of a photon, which is a light particle, and something called Planck's constant to determine frequency, also wavelength, and color of light either given off, or we could also do it to be absorbed. Now, just again to quickly review, if electrons go up to a higher energy level, the excited state, they're going to absorb very specific energies and therefore absorb specific frequencies of light. When this occurs, an absorption spectrum is produced. And you can see there by the black lines, those are the wavelengths that get absorbed during this transition. Electrons can then fall back down. Remember, the excited state is unstable, so they fall back down to represent the ground state, and when that occurs, it emits those specific energies of photons or light particles, and therefore emitting specific frequencies of light. An emission spectrum then shows which colors are emitted with those color lines, and in a lab this week we'll be looking at those more closely. Now, Bohr's model of an atom is not just conceptual, as we've done up until this point, but it can also be quantized. We can utilize information about the light and complete various calculations about the element. So in Bohr's diagram, we have our principal energy levels, but they don't just exist as rings, around the atom, as we know. We can relate them directly to specific energies. And we're going to be using this chart. It's in your honors reference table that you were given in class, that we can look at the different energy levels and relate them to specific energies and find the differences between them and do various calculations with those. So we're first going to simply determine the energies equal to the difference between the levels. Now, according to Bohr, an electron could go into a higher energy level by absorbing only specific amounts of energy. The difference between two levels jumped. So if I go from n equals 5 to n equals 2, I look up each of their values on our chart, and then I'm simply going to subtract them. I prefer to subtract them so that I do the smaller number minus larger number so I get a positive value, and then I can just make sure I always state whether it's being released or absorbed. So to go from 2 to 5, we're going to absorb 2.86 electron volts. Now, if it goes back down from 2 to 5, we're going to see that it's going to also be equal to 2.86 electron volts. Now, that's if it goes directly from 5 to 2. However, it could be broken up into 2 photons of light, first falling from 5 to 4, and then from 4 to 2, or even 3 photons. However, the total is always going to be equal to that 2.86 electron volts. So now we're going to take that and determine the wavelength that could be absorbed or released. So as the energy in a hydrogen atom is absorbed from, it should say released from n equals 5 to n equals 2, what wavelength of light is released. So just make sure in your note packet, I was able to change this one, but I didn't catch the one before. Make sure those both say released. What wavelength of light is released? So first we just have to find the energy, which we just did in our previous slide. So we're still going from n equals 5 to n equals 2. So we showed this calculation before, how we got the 2.86 electron volts. However, if you look at our formulas that we're going to be using, Planck's constant is in joules, which means we have to take our electron volts and convert it to joules. So we're going to do this using dimensional analysis that we did back in Unit 1. We're going to start with our electron volts, use our conversion factor. Remember, if we start with electron volts, you put electron volts in the denominator. And in solving this, we now know that our amount of energy for this transition in joules. So now that I have that in joules, I can then go ahead and actually use the formula that's going to relate energy and wavelength because the other two variables are constant. So we're going to use this first part of the formula that relates energy and wavelength because H and C, again, are constants that are over in the middle here of your equations. So we have then Planck's constant, the speed of light, divided by our energy. I've rearranged the variables here by cross-multiplying and then dividing by E. So my energy is then going in the denominator. And then I can get my wavelength, and the unit is in meters. So again, once I find the energies, I can just simply go ahead, find the part of the formula that relates my two variables. Because I wanted to know my wavelength, I was able to use energy to get to wavelength. And again, this was from rearranging the formula. Okay, so now we can also determine frequency and the color of light that's actually emitted when this transition happens. So as the electrons in a hydrogen atom falls from n equals 5 to n equals 2, what color of light is emitted? That's our goal, is figuring out the color of light. So we're going to complete several steps. We've already seen these first two steps. So finding the energy to be released, which is the 2.86 electron volts, and also converting from electron volts to joules in order to use the formulas in our reference tables. So the new part then is we're going to use the determined photon energy, so the capital E, and Planck's constant to determine frequency, which is represented by the letter V. So here we have our formula, and again I'm taking E is equal to HV, so I'm taking the part of the formula out of this combination here that I would like. Remember, I'm looking for frequency, so I'm going to solve plugging in my energy and the Planck's constant to get my frequency, which is in something called hertz. All right, so now we're going to apply that, okay, and look at our other part of our chart on our reference table. If this is my frequency, I basically found it, and then I'm going to see where this falls between, which ends up being between the two kind of starting and ending points for violet. So then I know that violet was given off. So whenever you're looking for the color of light, you have to always first go to frequency and then use that in the chart to figure out what color of light or what other type of electromagnetic energy is produced. Now we've been doing the transition from n equals 5 to n equals 2, and the line seen as the electrons that return to n equals 2, in like the examples we just did, in hydrogen is known as something called the Balmer's series. These are always visible light. However, when electrons do fall back to n equals 1, the energy is too high for visible light, so we can't actually see those transitions. Okay, so that's it. We're going to practice this basically for the next 2 days to work on these calculations. Make sure you get comfortable with them before moving on.